Okay, so again, um, the the differential scattering rate into a particular solid angle element, df d omega, should be proportional to the intensity of the beam and the number of target atoms that the beam intersects. Okay, and we call this proportionality constant, we call d sigma d omega. Okay, which is the which is called the differential cross section. And the differential cross section contains all the physics. Okay, the differential cross section tells you for each atom coming in, for each target, for each beam particle coming in, how it's going to be interacting with a single scattering center or single atom in the target. So this is where all the physics goes. So for example, if the interaction between the if the beam particles are charged, okay, like alpha particles, and the target, the scattering centers in the target are nuclei, which are also charged, then the d sigma omega here, the differential cross section, is going to be related to the Coulomb force that would which is going to deflect the target, the beam atoms, as they come and interact with the nucleus. Okay, so all the physics contained in this differential cross section d sigma d omega. So it's a characteristic of the interaction of the beam particles and the target and the scattering sites within the target. Okay, and if you look at this and we realize that the beam intensity has units of number of particles per unit area per unit time, and the n is just number of particles, then what we realize is that sigma here, the units of sigma has to be units of area. Okay, and when we talk about scattering, this is generically what we're describing here is called scattering theory, and particularly when we talk about scattering off of of sort of small fundamental particles like nuclei. They're not fundamental particles, but small particles. A common unit for sigma, for the cross section. Sigma is a cross section. We call it the cross section. D sigma d omega is a differential cross section. Sigma is the cross section. So common unit for the cross section is something called the barn, and one barn just is defined to be 10 to the minus 28 square meters. Okay, now we've basically set up the problem. We've basically given most of the background that's necessary in order to now kind of go through a derivation, a calculation of how, in the particular case of Rutherford's experiments, where he had these alpha particles, that is helium nuclei, so the two protons, two neutrons, shining a beam of alpha particles on a very thin gold film, very thin gold foil, I should say. Basically, what we're going to do now in the next lecture is to using this formalism which we've developed now, the cross sections, solid angles, differential cross sections. We're going to work through how Rutherford showed that that the results that he had, this anomalous backscattering of alpha particles, that is, particles scattered at large angles greater than 90 degrees relative to the initial direction, how that basically leads to the conclusion that you have a very compact nucleus where the positive charge resides.